Hello to this live session. Today we're continuing our doing a SOBEL or a kernel, custom kernel in HDL. And right now we're working on doing the multiplying the coefficient to every value. We're trying to do it using shift values and adds to avoid using a DSP, because DSPs are useful but spread out. And as we scale up, the DSPs will become a bigger constraint. So I'm trying to do this all on HDL, which will help with resource and timing and whatnot if we avoid the necessity of using a DSP. I think we should be able to. So we're going to extend this to 9 stages, test it works in simulation, and then we're going to try to parameterize it and see if we can do 15 stages or 25, 5 by 5, and maybe try to do a 10 by 10 and see how that goes. And then we got to figure out how to do summation. We'll probably do the summation next time. So we're just going to build these stages going forth until we are at stage 9. Well, actually, it'll probably be stage 10 in this. So we're just going to copy this and move this forward. It's probably going to be a little bit boring as we just go through and do this all by hand. And then we'll have to figure out how to make this a little bit more efficient. That should be good. Oh, we want to do just one less bit. 12 down to 0. Shifted one more. I'm not sure how we're going to do that. I guess you could do others, and others equals 0. That might be a way to do it. Set the line up properly. Not sure. We're going to have to figure that out the fun way. So if we do it like this, 5, 6, 7, 8, 9. Yeah. Start here. Stage 5. Five is not declared. Oh, it's supposed to be 4. Well, 4 is not declared either, so. Control D. 4, 5, 6, 7, 8, 9. Might not need that many, but. 5, 6, 7, 8, 9. Then we need sign. 6, 7, 8, 9. 7, 8, 9. See how far that gets us. That's all right. It's that we need to change. 2, 3. So this needs to be 6. We want 5s there. And 4s across everything else. Okay, 4, 4, 4. That would be a 3. 3, 4. And we're going to do 11 down to 0, 0, 0. Let's see if we do others. I mean, we could do 2 unsigned, 0, comma, and what? We want it to be 4. We could do that as a potential option. to increase paste that number in those things. See how that goes. Okay. So we're gonna do stage 7. Move these to 6. These are gonna be 5, 5, 3 to 5, 5, 5, 5, 5, 4, 4, 5, 10 down to 0, and 5. Stage 8, 7, 7, 7, 6, 6, 6. I think there's only one more after this because you can't go to the 7th or the 8th bit, not the 7th bit. 5, 5, 5, 9 down to 0 with 6 zeros. Five. Okay. So this is going to be 8, 8, 8. Stage 9. Six, 5, 4, 3, 2, 1, 0. I think we can only go to 6, right? 0 to 6. Because if we use 7, 7's the sign. Yeah. The 7 would be the sign bit, whether it's negative or positive. Well, we can keep that stage. And if 7 is positive, signed. We 7, 7, 7, 6, 6. We do the absolute value. There's just still one more bit, and then we have to negate it. Okay, let me see. Let's see if we can find a 2's complement calculator. So, 2's complement calculator. Trying to think. Enter. So we do. Three, 1, 2, 3, 1, 2, 3, 4. So you can do one more negative. Okay, so we want to do this. So we want to do it with this one more time for the 7th bit of the value. Then negate it, then shift it right. Oh, we have to shift it right arithmetically if we do the shift right. Arithmetic shift. Okay, so we do want to do a 7-bit here because that's going to be the top bit. And then we're going to do the 6, 8, 7. Okay, zero, 1, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. Okay, now we're gonna do the negate stage, which will be stage 10, negation. And we're going to say if coefficient sign is 1, then we basically just want and 7. Okay. So we got that going. Now let's go ahead and run the simulation. Do I have the simulation in another file? Oh, apparently I do. Here we already have it. So let's see. Sources. Okay, well, let's just recompile it here. I guess we already have everything we want. Oh, we have to add the other signals. We have, where's our launch script? Oh, there's our launch script. We have our launch script here. Let's go ahead and do 4, 5, 6, 7, 8, 9, and then we'll have to create 200. That seems about right. Here. So let's remove these. We want the window comp. We're gonna add those two waveforms, and we want them to be radix sine decimal. And then we're going to do this. Did we not get to that stage? Let's see, operator. What is this? Okay, that's 8. 1, 2, 3, 8, 10, 12, 21, 24, 27. Cool, we got that working just fine. Now let's throw in some bigger values, shall we? We can try 128. Negative 128. Negative 1. Negative 10. Negative 20. I'll leave those as, let's see if it accepts those hex numbers. Oh, wait a minute, those are hex, not des. Oh. Okay, if these are hex, I want 7F, FR 80, FF, E F 9. Okay, so 127, -1, -4, -14. And what's that value? 27. Okay, that's cool. So it looks like it's working. So now we want to create a way to parameterize this to make it more stages, to have more coefficients and whatnot. Okay. How do we do this? Well, first, let's get rid of this other project real quick and just open it in that one project. So to do this, we're gonna have to open this. We're gonna have to have constant kernel size real C HDL real number. We're gonna call it a real, and we're gonna set it equal to 3. And then we're gonna have a constant kernel array size, and that is going to be a real as well, and it's going to equal kernel size times kernel size. Do I need to do real integer? How do we do it? Let me just say real. Only positive integer. Oh, we can say positive. Oh no, we want natural? Is that what we want? Do positive. Okay, and be this -1, right? That's how tall we actually go. So we needed only 9 of here and 8 of those. So what we need to do is we need to create a new type, right? We're going to type t window array is array from, we'll hard code these right now to figure out how to do it. 0 to how many we needed? 8 of those, right? No, did we actually reach the 9? We actually reached 9, so those need 9. So 9 of T window array, right? And then we're going to do signal window reg is T window array and we need an others, another others, and we'll go through here. Oh, there is no. I don't have a common one yet. So something like that. So, and then we need a Windows COM of that same thing, right? Do a signal window COM. And we're going to do a T sign array, a T value array, and it's going to be of T sign and T value. Actually, we just, this one doesn't need as many others. So T sign array. And then let's do a co value. And we're gonna so theoretically we can get rid of all of these. Or these guys right here. Your co value. You're gonna want that as well. Okay, so let's get these initial ones done, right? So this is gonna be 0, 0, 1, 1, 0, 0, 0, 0, 0. So we're going to keep one of these, and then we're going to parameterize everything. What's that last one? So we're going to do stages 3 to n here, right? So we're going to do a for I in we're going to do for I in we're starting at 2, right? Or no, we're going to start at 1. And there's a 0 there. So we're going to do 0 to, what was the top stage? It's going to be a 6, right? 0 to 6. That'd be 7. Yeah, 0 to 6. Loop. End loop. So this is going to be I plus 2. I plus 2, I plus 2. and this is going to be I plus 1. Oh, no. We have too many i's. These need to be j. 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 And then, yeah, and then this is going to be straight up J. Okay. And now, let's just... I is not a signal. Eight. If I put that same line down here, what happens? Oh, boom, that's what's happening. 9, 8. Seven, 7, 7, 7. Okay, so we have this. Now we're gonna have to, let's test it real quick, and then we're gonna parameterize it so we can then do a 5x5 and a 10x10 block. It's going to be ridiculous. I'm excited. Those signals don't exist anymore. I have to delete those. So objects, we want window comp add to waveform. We want this to be a radix, sign decimal, tickle cancel. Let's go back to where we had our stuff. Oops. Whoopsie daisy. Oh. Sorry, did I not specify I wanted this sign decimal? Okay. So now we have an issue. Oh, I know what happened. I know what happened. Right here. This was supposed to be speak to unsigned what, 0, comma j plus 1. Oh. And this was supposed to be yeah, 14 minus j. Why not just do it that way? Recompile. Let's get this working. I'm excited. Parameterize this. We can get the 5x5 working before the day is over. That's great. Next, we have to do the parameterize the summing tree. That one is going to be interesting. Boop, 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 boop. Oh, something went wrong. Something went very wrong. One, 3, 7, 15, 31, 60, 31, 27, 255. Can we get this as a radix sign decimal, please? 127. So what happened at last shift? One, 3, 4, 15, 16, 27. We do one too many stages? Oh, I think I know. Right here. Ugh, this is supposed to be j plus 1. There's no hard-coded values anywhere in here, right? Except the 14. Okay, that's good. Let's try this again, shall we? Okay, do that after the stream. So, now let's rerun it. And it's working. Sweet. Now, what do we need to do to parameterize it? So these base values can stay the same. And what is this? This is going to be -2. No, that's the same, right? This is a value that changes, not this, right? And it's only that would change because we're increasing the window size. That doesn't increase the multiplication, it just increases a little more multiply. The summing tree is what's going to be a pain. But we just have to change this value, right? So if we go to package and I say kernel array size, and I go like, oh, you're now kernel array size. You're now kernel array size. You too. And we're going to do this kernel array size. Because the coefficient times everything in the window. It's the adding tree that's going to be a pain. Adding tree, we're going to have to do something funky like that. Okay, so let's see if that works. Should get the same thing. Then Okay. So that worked. Now, if we go here, and all we're going to say, oh, well, let's do a 5 by 5, shall we not? Shall we not? We're going to do a 5 by 5. Let's see what happens. Oh, these windows are going to get so much bigger. 9, 10, 11, 12, 13, 14. Should make like a tickle script that just goes through these and does like individual ones. Okay, we went from 9 to 18. Just to prove that it works, we'll just do 9, 10, 11, 12, 13, 14, 15, 16, 17. And now to 24. Oh, sweet. So I'm curious of what resources this requires. And it looks like it runs beautifully. We just parameterized our window size. So what we're gonna do is we're gonna do a 3 by 3, do it, and do a 5 by 5, do it, and synthesize it. So we're gonna run a synthesis. It's gonna be angry or whatever. I want to see how many resources take. This is going to be, besides the VRAM, this is probably going to be the most resource intensive thing. And so we had our 5 by 5 was taking up 20,000 LUTs. So let's see what our system is. Let's open the synthesized design. Yeah, we're going to have to figure out how to do the summing tree next time. I'll have to think about that. Crunch it down. I could just make it redundant and just add zeros to things. That's going to be interesting. So let's do reports. Utilization report. Interesting. Do we not have empty? Why are we empty? Is it because we don't have an output? We don't have an output. So what is our output going to be? Output out. You know what? We're just going to put these all in my type package. Voila. And we're going to have a Windows 6 as our output. Nope. And that output, we're just going to assign it to our last comp, which is going to be that one. Boom. Okay, we're going to run synthesis again. We don't have an empty design. Should probably do out context synthesis to even get a better report. So we're gonna close this design. Synthesis settings. I wonder if I could do like out context synthesis build. Out of context, it's not one of those. Let's go ahead and open it. Cancel. We got a net list, we got a nets. Cool. let's do report utilization. So, I don't care about the IV. So, this was at 20,000, we're at 1575. So, I mean, we're probably at a 10x reduction. Let's see what happens if we go bigger. Run synthesis. So, I mean, we still have to do the summation tree, but the summation tree should be much smaller compared to this guy. And the line buffers, while they take memory, do not take much logic. So, and once we do the summation, we can do some simple stuff. But say if we do this for every channel, then it'd be interesting, right? So if we take the 5 by 5, multiply that logic by about 3, then we get what we tried to do in the HLS. Which I think it was around, 22,000 slices. And I just want to see how this compares from HLS to reports utilization. So that was about 1,500. Let's see what this one is. 4,300. Now if we did that, so this is just for one color minus the overhead. So let's say overhead adds another 2,000, so maybe we're looking at 6,000, times it by 3. In all honesty, HLS was not that bloated. HLS will probably be about the same structure. Really interesting, but we get better latency, but probably not much. I think in this situation, my HLS is probably on par with these tools, with what I'm doing here. So let's go to the extreme. Let's do 10 by 10, which is, I feel like, a more theoretical, a medium-sized filter. I feel like you go to 2020 or higher. Let's run synthesis. Okay. And what I can say here is that HLS is actually performing well. Once it's toned down and whatnot. We could do a 5 by 5 just on grayscale. That would probably decrease it down to a doable value. Interesting. This is interesting. How's it going? Synthesis finished. Zeros, errors, and tons of warnings. We gotta. Yeah, let's see what we got here. I'm curious. But I wonder what the optimization state would do to fix it up. Yeah, look at that. That's a pretty beefy system right there. But it's doing a 10 by 10, which is which is 10,000. 10 times 10. Oh, it's just 100, which is 4x bigger. 4x bigger. So we're probably looking at that size for the other things. But wow, I'm gonna have to say HLS did not necessarily do a bad job. A little bloat maybe, but if I wrote it, it'd be about the same. So this is interesting going forward. Now that we see my custom HDL is about the same size, I mean, what else is there to do but to push it, build it, and compare utilization numbers in a place and routed step to figure out what was lacking or what was not lacking. Yeah, so we're going to try to build it in HDL and compare the final results, but I think HLS did a pretty good job. So next time we'll try to do the addition tree, or not the addition tree, the summation tree with a variable length. That's going to be hard. I don't know how I'm going to do that, but that'll be a fun project to look at next time. Okay, guys, I think that we're going to end our video there and state with the kind of the final thought that Vivado HLS ain't that bad when it comes to the results if you can get it, if you can constrain it correctly. Thanks for watching. See you later. Bye.